And we should be rolling now.
Okay, great. Thanks, Fred, for the introduction, and good afternoon, morning, or good night, everyone, depending on which time zone you are in. For me, it's morning. So I'm Stefan. I'm giving the Parton shower introduction here, and yeah, let's jump right in. So the goals of this lecture will be to give you really very much a bird's eye overview of where the field of Parton showers is at the moment. Showers have been a topic of really intense research over the past decades, many decades actually, because they connect theory and experiment, and you heard a lot about this in Stefan's introductory lecture on Monday already, and also in Dave's lecture. And they essentially connect the high and the low momentum scales in the event simulation. They are supposed to generate a final state that's fully differentially, so very detailed, essentially, being coupled to heteronization eventually to give you a realistic picture of the event. But at the same time, they are, of course, containing solid QCD theory. And because of this, this twofold task to be precise and to some order and perturbation theory, and also being fully differential, which is very complicated because it's very high dimensional phase states that you're trying to fill, there are some concessions that we need to make in order to get things done, and I will go through those in detail. Interestingly, there is much interest still after 4 decades in understanding the interplay between Parton showers and analytic resummation, and I will hopefully be able to cover this. And also in finding new and better algorithms that allow an extension of these Parton showers to higher formal accuracy, let's say next to leading logarithmic accuracy or so. And what's interesting is that to some extent also the definition of accuracy itself is still being worked on and debated. So what I will try to do in this lecture is I will try to give you the background that allows you to understand what is actually being discussed in past and present Parton shower literature and why this is important. And you will have the tutorial as a chance for an in-depth discussion of the basic concepts that are presented here in the lecture, both for showers and for analytic resummation. And you can do, you can take your pick. So it's kind of a la carte. If you're interested in this, you can pick it. If not, you can choose a different tutorial, and you can choose between doing this tutorial and on analytic resummation or on Parton showers as you prefer. What not to expect is all the latest and greatest plots. I think this is pretty much true for all the lectures. If I wanted to do a survey of everything that is out there, it would fill the entire time of the school and we wouldn't even be done. So there's still much to do, so let's jump right in. I have a couple of books for the background reading here, and one of the nicest ones is certainly the classic review of Alice Sterling and Weber. If you are much into calculating things yourself, there is this nice book here by Rick Field, which has a lot of the calculations done very explicitly. And you can look up any factor of 2 or any 1 over epsilon as you prefer. There is the introduction by Michael Peskin that I will make use of, and then there is a more recent write-up in the proceedings of the TASI School 2014. And in particular, when it comes to simulating things, which this lecture is all about, because it's about Parton showers, there is the Pythia 6.4 physics and manual, which is really more physics than manual, and it's a really large write-up of essentially all the physics that is contained in Parton shower event generators. And I will only give additional references on the slides if they are not covered in these books already. So as I already said, you will have the chance to get your hands dirty in the tutorials, and the links are given here. You've already been told about this yesterday, and yeah, we can talk about this in the afternoon or tomorrow. Actually, this one is tomorrow because today there's a shorter tutorial in that place. Okay, so we will start with a heuristic picture of Parton showers. I will just give some hand-waving introductions of how they are constructed and be a little more detailed than what was covered in the introductory lecture, as far as the splitting kernels and other things are concerned. We go over the technical ingredients and how to implement them. And then I will try to derive the Parton shower picture from semi-classical perturbation theory. I will take what we get from there and introduce the concept of color coherence and higher order effects, certain higher order effects, not all higher order effects. Try to make a connection to analytic resummation and end with some notes on forward and backward evolution, if we have the time. Okay, so what is a Parton shower? Let's take a heuristic view. You already heard from Stefan in the introductory lecture that in order to get the Parton shower up and running, you essentially need to make two assumptions. You can have a Parton branching, and this Parton branching can occur in a way that you, colloquially speaking, observe the two decay products of the partonic decay individually in your detector. So let's say these two partons that we see here appear in two different cells in the detector, and you can actually resolve the difference between them, so you can resolve them individually. You can see them, in other words. At the same time, you may have a Parton branching where you can't distinguish the outcome, even if you have two partons, or if you have a Parton like here that recombines with the original radiator. And in this case, we would call this an unobserved event or a virtual correction. And the second basic assumption is that whatever happens, it conserves probability. In other words, in the sum of these two possibilities, the chance to change the overall cross-section of the event, for example, is vanishing. So you're not allowed to change the cross-section. Now, the immediate consequence of this is Poisson statistics. Let's assume that this branching here occurs with some decay constant. For now, let's assume this is a nuclear decay, which we call lambda, some decay probability. And if we go to QCD, we have a quark here. I can radiate many gluons. I can do this n times. Okay, so I have n gluons here, and in this case, I get that decay probability to the power of n, but because the final state is indistinguishable, I have to divide by a symmetry factor, and that's my n factorial. And when I look at this term, and I consider that I can have any n, and I sum over all the possibilities from n equals 0 to n equals infinity, you will recognize that series. It's an exponential series. So this will diverge if lambda is only large enough. And this is actually what would happen in practice, as I will explain in a couple of slides. So in order to make this finite, we have to add the corresponding term that, that brings this back to unity, because I said I'm not allowed to change the overall cross-section. So this e to the minus lambda will make sure that in the sum over everything, I observe a unit probability. And in the context of a Parton shower, this e to the minus lambda is called the Sudakov factor. Okay, not exactly the same as the Sudakov form factor, but there is a connection between the two. Now, the only remaining task, if you will, in order to get a Parton shower done, so it will be done quite quickly, is to construct lambda. How do we do this? Well, we already said that we want to observe a partonic decay. Sorry, a Parton decay. So what we can do is we take the n+1 particle cross-section, we divide it by the n particle cross-section, and because we have to parameterize somehow what our decay time is, we take the derivative of the cross-section with respect to some t, which for now I will leave unspecified, so that's my decay time. And in the end, we integrate over t from some upper starting scale to some lower stopping scale. Okay, and this will be my lambda. So this lambda is actually a lambda that depends on two scales. Okay, so pictorially, this is shown here on the right. So you have a large final state with n+1 particles. This is the n+1 particle final state, you write this as some n particle final state and this branching process here, which depends on the momentum transfer in that pattern when it goes from here to there. And then everything also depends on the virtuality of that propagator here, of that intermediate pattern. This is what my decay time will eventually be. We just call it T because it identifies so nicely with evolution time. Okay, wait a second. Okay, I'm still sharing, right? Because my iPad just did something funny.
Looks good.
Okay, great. Okay, so this splitting function here, as we call it, this P of C, depends on the Parton configuration. So if I have a quark-to-quark transition as here, then it looks like on the right-hand side. If I have a gluon-to-gluon transition, we get this one. And what's interesting is the structure of the equation. So first of all, we have a logarithmic integral here, which is really because
No, I think your iPad has stopped sharing. It also didn't share anymore, or it showed up a static picture.
I see. Okay, let me try and restart this. Oh, I think Zoom actually quit. Okay, I think I have to rejoin. That's kind of annoying. Sorry about this. Okay, let's get this started again. Ah, I know what happened. So sorry about that. Apparently this thing decided to update. Alrighty. Okay. Sorry about that. I think this thing decided to update. Alrighty, we are back. Okay, so what's very interesting about this is, okay, let me try and sketch this again. That over here we have a logarithmic integral, and this is really because the hard matrix element is proportional to 1 over t bar, which comes from the propagator factor. And then what's another point is that when you look at the z integral, there is another leading term in the splitting function, which is shown here, which is actually the same between quarks and gluons, and we will go into some more detail about this later on. So as your first exercise, I'd suggest that you discuss in the recitation session why that term actually appears both in the quark and the gluon splitting function. And it does not appear here in the gluon to gluon bar splitting. Okay, so when we add partons through a Parton shower to an existing configuration, there are a couple of important things. One is that the on-shell conditions must be maintained, which means that when I go from this n particle state here to the n+1 particle state here, both must have all external particles on shell, because otherwise we cannot meaningfully perform a gauge invariant calculation in perturbative QCD. Form momentum must be conserved because I said we want to perform a faithful simulation of the entire final state, and color should be preserved. And whatever that means, I will go into some detail later on. Okay, so let's look at the phase space. Let's take an example where we have a particle that I call ij tilde, because later on it will decay into two particles i and j. So these are just labels for my momentum. And we have a particle k tilde. They have some momenta, pk tilde, pij tilde, and we map them to new particles, as I said, i, j, I, and k. And what's important is that these particles, or this branching, is supposed to be resolved. So there is supposed to be a finite transfer separation between these particles. And whenever that happens, you can do a calculation, and you will find it at the bottom of the slide. I will just mention this in a minute. Whenever this transverse momentum is a finite size, then you cannot have all particles in this process on their mass shell. In particular, what will have to happen is that this particle here will have to have a finite virtuality. So in going from the left to the right, we have to create this virtuality for this particle and then essentially let it decay. It's like a two-body decay. And there's a quite standard method for doing this. You can say, okay, I take my on-shell momentum, I borrow a little bit of momentum from a different particle, and this is why I need to have this thing that we call a spectator particle here. And in order to conserve the mass, or in order to instate the right mass, there needs to be a prefactor here proportional to the virtuality that I want to create. And the point is essentially that p tilde squared is 0 for both this guy and this guy. And then you can show that when you have precisely this prefactor, pij squared will have the right virtuality. Now, because I want to be overall form momentum conserving, whatever I borrowed here has to be given back here. So the spectator is also altered. Okay. Afterwards, after I borrowed this momentum, I distributed basically onto the two outgoing particles. So this equation determines what these final state momenta will look like. And your second exercise for the recitation session will be to answer the question whether or not this momentum mapping is collinear safe. And if you don't know what that means, then this is also a great point to discuss with your tutor in the recitation session. Okay, so I already said that the on-shell conditions require that in this particular momentum mapping, we have this relation fulfilled. The transverse momentum is equal to the invariant mass, or rather the virtuality of the intermediate particle, which is this guy, times z times 1 minus z. So if I solve this equation for z, I obtain these solutions. And what this means in particular is that if I haven't yet fixed the virtuality of the particle, and it can be anywhere, but I have a minimum transverse momentum or minimum resolution for the Parton shower that I want to achieve, because I want to see, quote unquote, these final states up here, I and j individually, then the z range for the integration can only range between something that's larger than 0 and something that's smaller than 1. And this is an essential difference between the Parton shower and an analytic declub equation, where the integration range is always from 0 to 1. And we will discuss this difference in more detail later on. We'll not go over the initial state momentum mapping because you won't need this for the tutorial, but you will actually need this final state momentum mapping. That's why it's interesting to discuss this. Okay, the next point will be, again, from the heuristic point of view, how to color a Parton shower. So let's discuss the improved large density approximation. So something that's very useful that we always do, essentially always in the Parton shower world, is we use the color flow representation. What does that mean? Normally, when you have a gluon, the gluon propagator comes with a color factor that is delta AB, that just gives you a delta function in color space, right? So if you have a gluon zipping along here, it doesn't change its color on the way. Of course, there are vacuum fluctuations and everything that I'm not drawing here, but the gluon propagator essentially conserves the color between this point and where the gluon is produced and the other point where the gluon is annihilated. We write this using basic SU3 relations as a trace over the generators. So if I write out this trace, it's essentially this assignment of indices here in the middle. And then what I do is I introduce two delta functions to split this up and essentially cut this in the middle, quote unquote. What does that mean? Well, colloquially speaking, what I'm doing, actually quite literally, is I take that gluon, I insert a quark loop into the gluon, and I let the gluon continue. So mind you, this is just in color space, right? So there's no actual quark loop. It's just a way of thinking of things. And I have my gluon color index here. The gluon is in an octet representation. I have my gluon color index here. and I cut this in the middle, and I assign to that gluon the colors that I find in the middle, which is I assign I and J to that guy, and then I have K and L here, and because the gluon's not allowed to change the color, I have these delta functions here and there. Okay, this is very convenient, because now if I want to attach a gluon to a triple, so whenever I have a gluon, let's say, maybe an external gluon or an internal gluon, I do this, right? And I don't view the gluon as a particle with an octet index, but with two fundamental indices, these i's and j's, right? So if I now attach this gluon to a quark gluon vertex, I would essentially put another piece here and put the vertex there, okay? And put a KL index here. Sorry, I already used K and L, but you know what I mean. So this is what we have in this line. And then I calculate this block here, this entire block, as the quark gluon vertex in the color flow representation. And you know this relation, it's just essentially the Fields identity for the SU3 so I have open indices this time, so I don't have this trace that I had previously for the gluon propagator. And what I obtain is a leading color term, which is the first guy here. This is leading color. And this term is kind of sub-leading color, if you will, or next to leading color, depending on how your counting is. And they can be mapped to two different diagrams pictorially, this one and this one. And in these two diagrams, because the terms just consist of delta functions, you can identify a color flow. And if you distribute the indices right, it means that in the quark, in the leading color case, the color flows from the quark to the gluon, and then there's an anti-color flowing on the other side. In the singlet case, the color flows from the quark to the quark, and then there's a singlet gluon. Now, of course, in reality, there's no such thing like a singlet gluon, because it's SU3, right? So what happened? Well, what happened is that we took SU3, we split it into U3, and because we made a mistake, we have to subtract that, okay? So this subleading color term is just a manifestation of the fact that you did something stupid by turning SU3 into U3. But it is very useful because the U3 term is the leading term, and it allows a very nice identification of how the color flows. This is why it's called the color flow in the event. You can do the same thing for the gluon-gluon vertex. In this case, you will have two terms, this one, and they come with a relative minus sign. And your next exercise would be to explain why there is no 1 over NC term here. And also to think about, okay, I'll mention this later. Okay, so you may ask, okay, if I make this leading color approximation in the Parton shower, am I not making a big mistake? Okay, because 1 over NC is 1/3, it's a rather big number. You would rather not make a 30% mistake. Okay, so let's look at this term in more detail. It was given by this 1/2 delta IL delta JK, pictorially by this diagram on the right-hand side. So if we use this naively, we would actually, like I said, overestimate the color charge with which a quark radiates quite dramatically. So let's consider a somewhat bigger process, which is given by this blob here, and we square the diagram, so we have the same blob on the other side, and then we have a quark sticking out that radiates a gluon. Okay, and we square this thing. This thing is proportional to this term here on the right-hand side, which actually gives you a CF, and the reason why you get a CF is because there is a contraction of these two indices here, so that gives you the CF times delta IK. You can do this as an exercise. But now, because we replace our generators with the terms up here, it actually implies that instead of the CF, we get a CA over 2, and that's not so good. Okay, so just as a reminder, this is 4/3. This thing is 3/2. 4/3 versus 3/2 is not as big as the 1/3 that I mentioned before, but it's still a rather significant number. And if you have multiple gluon emissions, it accumulates. So what we actually do in the Parton shower is we treat the color flow at leading color, but then the color charge of the quarks are actually kept at CF, because otherwise we would radiate just way too many gluons. As your next exercise is the question, how would this look like, or what would this look like for gluons, or what would the gluon color assignment be? A great point to discuss during the recitation. Okay, so let's implement that algorithm. We're almost there. You already heard from Stefan in the introductory lecture that this can be done with inversion sampling. So I won't say too much about this. I will just introduce the Veto algorithm again, because it doesn't hurt to hear this. It's very useful in many real-life applications, because Poisson distributions are everywhere. Okay, in a Poisson distribution, the difference compared to a standard, whatever distribution you might want to sample, is that there is something like a differential decay probability, and there's the pseudocofactor that I introduced, which is just e to the minus integral over that decay probability over some time interval. And I will call this g of t. And the point is that if we know the primitive of that little g, which I call capital G here, so that's the integral of little g that appears in the exponential on the right-hand side, then we also know the integral of that calligraphic g. Okay, and that's because I can write the integral over the calligraphic g as the derivative of the pseudocofactor with respect to t prime, and then integrate over t prime. I'm sorry, this should be a t0 here. I will correct that. And this is just 1 minus the actual pseudocofactor. Okay, so you can solve this equation for t. A good question, maybe also discussed during the recitation, is why would I solve that equation for t? After you solve that equation for t, you find that you get almost the standard inversion sampling, except you don't get a random number here, but you get the log of a random number. Another good question to discuss during the recitation session is, what does that actually imply if you think about what the logarithm looks like? It's a function. It's just a teaser. Okay, so now what happens if you don't know your integral of little g of t precisely? Well, then you essentially try to find a simpler g of t. Let's say I have a function f of t, and that's very complicated. Let's say I have a 1 plus 5z squared plus 24z to the 4th or whatever, and I divide that by 1 minus z. And okay, I really don't want to integrate this, so I find something simpler. Let's say g of t is, if I have everything in the range from 0 to 1, I can safely say that this is the f of t is smaller than 30 over 1 minus c, and this is my approximation. Okay. Then I draw points according to this little g of t, which we just saw on the previous slide, and I accept this with a weight, which is just given by f of t over g of t. So this is like hit or miss. Okay. The question is whether that hit or miss actually also works in the context of Poisson distributions, and the surprising thing is that it does, and this is known by the name of the Veto algorithm. So you draw according to little g. So your probability for drawing a first point is what I just underlined. Then if you accept your event in the first step, you essentially get that factor w of t, which is kind of the accept probability from up here, and you're done. But it could also be that you reject your event, And the difference compared to a standard hit or miss is that you don't discard the event as a whole, but you continue starting from the present t. If you do this, what you obtain is the rejection probability, which is 1 minus the accept probability. And if you put these two terms here on a common denominator, you find that you can cancel this against this. So you get g of t minus f of t. And if you don't only have one rejection, but you have multiple rejections, you find that you obtain, because of this continue condition here, a nested integral for these multiple rejections. And you can perform the same trick as you do in standard QFT lectures when you talk about the time ordering operator. You can reorder this and turn these nested integrals into a 1 over n factorial times the basic integral to the power of n. And you know the series again, this is just an exponential series. So you find that this correction factor exponentiates, and combined with the a priori probability with which you draw the events, which gives you a g of t in the exponential, you find that, okay, schematically, this guy will cancel this guy, and what will remain is the f. So you have drawn precisely according to the distribution that you wanted to. That's the Veto algorithm. Now you use this to construct the Parton shower, and this is what you will do in the tutorial. You find a new scale t where the next branching occurs using this Veto algorithm. You determine a winner Parton, which is the one that branches, and select a new flavor. You select the splitting variable according to your overestimate function. That was your little f of t, or more precisely, it's alpha s times your splitting kernel that I introduced previously. And then you accept the point with the weight that is shown here. Then you construct the splitting kinematics, which I already talked about, and you update your event record, and you're done. You continue until everything falls below an infrared cutoff, where you can't resolve your splittings anymore. And if everything goes well, the result that you obtain will be independent of that infrared cutoff. That means you have to make your infrared cutoff small enough in order not to be sensitive to it. Okay. Are there questions so far? Yeah, I don't see any at the moment.
Hello. Yeah.
Okay.
Am I audible?
Yes, I can hear you.
Okay. So how you check that color flow of this splitting actually?
How I determine that color flow?
Okay, yeah.
Okay, so this goes according to the algorithm that I was showing here. For the quarks, because we are in the leading color approximation, remember there was a -1 over NC term here, in addition with this subleading color term. We don't have this, we just don't implement it. So the flow in the quark splitting is actually just what I was drawing here. Okay, so there's not much to do. Because we work at large NC, every color is unique. Okay, so this color gets a name, the red color here, and in event generators, you may know this from Pythia if you have seen Pythia already. We start with some color index, let's say 500 or so. So this is the color, let's say, the plus or minus event starts with. So there's a color connection here. The quark gets a color 500, the anti-quark gets an anti-color 500. And then when we radiate a new gluon, we get a new color. And because we work at large NC, this color can have any name, but it can't be the same as the previous one. So we give it another number, 501. And so it goes. Okay? And you can actually show, using the color flow representation of QCD, which I introduced here, that at leading NC, this is precisely the right picture. Okay, that is if you ignore all these terms here. Okay, for gluons, it's a little bit more complicated because you have these two terms here, this one and this one. So this is the okay, these correspond to two different kinds of flows, and we will hopefully discuss this in the recitation session in more detail, but you have to implement both of them. And something that we will discuss in detail is how to implement both of them so that you get the right physics picture. Does that kind of answer the question?
Yeah, thank you.
Okay. But idea is the same, right? A gluon would have two indices. Let's say this one is 500, this is 501. And then you get a new index here, which is 502. Okay. Let's say here you have 500, 501. And then you get a new index here, which is 502. So you branch this 500, 501 gluon in the left case to a new 500, 502 gluon and a 502, 501. And in the right case, it's different. And we will ask ourselves in the recitation sessions what the impact on the event structure is in comparison between the left and the right. Okay, it would go a little too far to discuss this now, but this is what it will look like. Okay, and please ask this question again in the recitation session where we'll have a little more time. Okay, more questions at this point. Okay, don't see any more, just shout if you have another question. So I will now go and discuss the effects of this. Okay, so we look at two classic distributions essentially. The first is the thrust distribution in E plus or minus, the other one is the differential 2 to 3 Durham jet rate, also in E plus or minus. And the first thing I would like to point out is that this is a distribution that goes over all phase space. So there is certainly a region where only hadronization is, or where mostly hadronization is important. And in the left distribution, it is roughly the region here. In the right distribution, it is roughly the region here. So they are dominated by hadronization. The transition is not quite sharp. There's always some boundary, but this is roughly where hadronization comes in. Then because it goes over all phase space, there's also a hard region. So this is where hard matrix elements become important, as you heard in the introductory lectures. The right distribution, okay, there's some wiggle room here, but it's roughly here, okay? And only what's left in between, only quote unquote, should be covered by the Parton shower. Now you will hear in the next lecture by Simon that you can actually, like I already indicated here, you can actually wiggle a bit, right? You can, because the Parton shower is in a certain approximation of an all orders calculation. In perturbative QCD, you can shift things around between the hard matrix elements and the Parton shower. So this boundary is flexible. But the point is that you can't wiggle so much between hadronization region and Parton shower because there are hadron masses and they are fixed. They are measurable. So on the right-hand side, this boundary here is essentially determined by the B quark mass, or by the B hadron mass rather, and the same is true on the left-hand side. But what's quite striking is that over a very large dynamic range here, both on the left and the right-hand side, the Parton shower describes the experimental data, and the ratio between the Monte Carlo and the data is at the bottom, extremely well. Okay, so the dynamics, kind of the evolution of QCD between high and low scales, which is what the Parton shower is supposed to describe, is described very well. It's also describing the hard regions very well, but that may be not so surprising because it's E plus or minus, and things are always easy on E plus or minus. Next example will be Z-boson production at the Tevatron. For those of you who still know the Tevatron. So we look at the transpose momentum of the E plus E minus pair. And we find that the Parton shower also in this case, it doesn't describe the distribution so well, but it describes it fairly well up to a certain point. So anybody an idea what this point is?
Is it the Z mass?
Yes, precisely. Thank you very much. So you remember I have this equation dt by t dz alpha s over 2 pi p of z. And there was actually a very important information here which was contained in this upper integration boundary. In our case, thank you, Lois, this is the z mass. So the Parton shower, because this t is essentially something like the transverse momentum, cannot generate any transverse momentum that is larger than the starting scale. And because we set the starting scale to the z mass, the distribution will just fall off as soon as we reach the z mass. And the reason why there is a bit of smearing here is because there are contributions from subsequent splittings, and also the z mass is not quite sharp, but there is a bi-Wigner distribution, and that's the tail that you see. Okay, last thing I want to discuss is PP. So now we go to a present-day collider, LHC. You're taking the leading jet pair, and you investigate the angle between the two, and you plot this. Again, over a very wide dynamic range. So the dijet region, the back-to-back region is here at delta phi equals pi. So this is only the azimuthal angle. The multi-jet region, where you have kind of the situation from the bottom is down there. And then in between, you have whatever you have, right? And what's very surprising, is actually shocking, is that the pure Parton shower, there's no matching or merging going on in this plot, describes the entire dynamic range. And we can discuss about why this may be in the recitation session, but it seems to be that Parton showers are extremely flexible tools that capture much of the physics that occurs in these collisions. All right, so let's look at that in a little bit more detail. What is a Parton shower actually? Let's take a more fundamental approach. Let's say we take a classical point charge that moves on a trajectory, which I parameterize as a point in space-time as a function of a line element s, and I will turn this line element into a time. And what if I have a classical point charge? That means the particle stays there, it's not destroyed, and no new particle of that type is produced for the moment. So this will be a conserved current. Conserved because the particle is not destroyed, a current because it has a charge, okay? And the way I can phrase this current is I give it a coupling, which comes from some coupling constant alpha, and I integrate over the time, and I take kind of the velocity of that particle, and the current at point x will be determined by looking at whether the particle is at point x at any point in space-time. That's parameterized by this four-dimensional delta function. So I Fourier transform this to momentum space. That's actually a super easy Fourier transform because I have this delta function. So what will happen is that this y of t will just come into the exponent here, and I'm done. So now I assume that this particle moves with a certain momentum PA, which is constant, if the time is less than 0. It receives a kick at the origin, and we will be unspecific as to where this kick comes from, but what is important is that the kick is instantaneous. It happens at the origin, at the time equals 0. I can always shift time around, so it can happen at any time, but it's instantaneous. And after the kick, the particle moves with PB. Then I can write my y of t as so. I essentially take the time times the velocity of that particle, and the velocity changes both direction and magnitude potentially at time 0. Now, in order to make things work in this integral up here, I have to introduce a little regulator, which is my epsilon here. But the rest of the integral is super easy. I just take the time, and because PA and PB are assumed to be constant, I just have the time up here, where you all can perform this integral. I just get the Jacobian into the denominator from this exponential function and this exponential function here, and what I will obtain is a classical current. Many of you will have seen this classical current in a different context, and we can discuss where it comes from in the recitation session. The important thing is that this current is spin independent. I did not have to make any assumptions about where the particle comes from, what kind of quantum nature it has. It's a classical particle and it's conserved. Okay, so these two things are essential. Now we add the actual quantum part of the thing. My current can now create gauge bosons. And in order to create gauge bosons, I need to have a gauge field, and I need to couple my gauge field to the current. And I do this in the standard way that you always see in your lectures. I just use a minimal coupling, and that will be my Hamiltonian. Once I have that interaction Hamiltonian, I can write down the probability of not having an emission as something that I will call the vacuum persistence amplitude. I'll label this by W A to B. So my particle goes from momentum A to momentum B, and it's a vacuum amplitude because I have the vacuum here, and I can insert into this vacuum any number of interaction Hamiltonians. That means as my current moves along from point X to point Y or whatever, it can create any number of fluctuations from the vacuum, but the important thing is that at the end, I have to reach the vacuum again, okay? Because I want to contract this with the cat state, with the brass state on the other side. I can expand this into a power series by essentially singling out the terms which I will label with an superscript n that are proportional to g to the n. And what I will also do for convenience, I will pull out a factor 1 over n factorial, but that's just a convention for now. So something to realize is that the 0th order term, which looks like just the product of the vacuum with itself, is 1 by definition. That's the normalization condition for the vacuum. And my first order term, because I have nothing to contract this gauge field with, is actually 0. This operator will annihilate the vacuum. Okay, so once I know this, the first actual contribution is the second order term. In the second order term, because I had a time ordering here, I have the time ordered product of two gauge fields that are sandwiched between the vacuum states. And they get multiplied because I had the minimal coupling to two currents. I guess you will all recognize the structure that is appearing here. Anybody? Anybody wants to shout what happens there? So this is the Feynman propagator. Okay. What this means, this time order product of the two gauge fields is just the Feynman propagator for the gluon between points x and point y in position space, not in momentum space. Okay. And I already showed on the previous slide, this thing is a virtual correction because we want to reach the vacuum again. So the gluon is produced and again absorbed by the classical current. This propagation between point x and point y is, as I said, described by this time-ordered Green's function. This time-ordered Green's function has a name, it's the Feynman propagator. And you can go to your QFT lecture and see that I can decompose this gauge field into a dynamic part, which is given by this exponential here, and a kind of a part that's only due to kinematics, which is this part here. And if I go over the two gauge fields, I will obtain a sum of products of polarization vectors, which encapsulate the spin structure of the gauge field. And in the end, after putting everything together, I will obtain the familiar form of the Feynman propagator in position space, which is why I will have to perform this Fourier transform here. Okay. Important thing is you get this sum over the polarization states. Okay, now I insert this Feynman propagator into my vacuum persistence amplitude. I have it here and kind of here. Okay. Remember, you had to contract this with the currents through the minimal coupling. And what remains eventually after you perform your integrals over positions x and y is you get a fully momentum space result, which has a propagator term and some product of currents times polarization vectors. Now you can use the completeness relation for the polarization vectors, for example, an axial gauge, which is given here, and insert this into the above equation and work out that factor here. And what you obtain is this term. And many of you will recognize this term. And for those who don't, please ask again in the recitation session. It's an important term. Your next exercise is actually to derive that term using a different gauge, for example, Landau gauge. In order to perform the remaining integrals, we actually have to do some tricks. We have to go to dimensional regularization. So we go to d equals 4 minus 2 epsilon, or introduce a cutoff. And Dave already talked about this in his lectures. And because we go to d dimensions, we also have to do something to the coupling. And this is done through the so-called MS bar scheme. We give the coupling a mass dimension in a very specific way, such as to also subtract a certain for pi and a certain Euler gamma. But this is convention. What's not convention is this term here, this mu squared. Okay. After we have separated out the infrared and IR poles and split them appropriately, and Valerio talked about this already in his lecture this morning, we are left with a purely infrared divergent result. So these epsilons in Valerio's language are IR epsilons. Interesting to note, there is a double pole here, there's a single pole here, there is a double logarithmic enhancement, and there are some constants. And then, okay, in the end, we want to send epsilon to 0. Therefore, we can ignore all the terms of order epsilon. And there's a minus sign up front, which is also interesting. Okay, so that's our second order result for the vacuum persistence amplitude. Let's look at the configuration where we don't reabsorb the gauge field quantum, but we let it free, basically. So this corresponds, for example, to the real emission term that I showed earlier, where you observe the two in the detector individually. But this time it's not quite like that, because we integrate over all phase space for these two guys. So you have both observed and unobserved states. Okay, it's not a vacuum anymore on the right-hand side. We start with a vacuum, but in the end, we will end up with something where a single gauge quantum appears in the final state. But again, we can insert any number of interaction Hamiltonians in between. By the way, I forgot to mention earlier that this structure that you see here is the same as what appeared in Dave's lecture yesterday, this Wilson line with which the Parton distribution was defined. So again, let's expand this into a power series. We pull out a factor 1 over n factorial, and we define these terms, individual terms, as to be proportional to g to the n. So we sort by the coupling. We perform perturbation theory. Okay. The 0th order term this time is 0, because if I don't have a gauge field here, I have nothing to contract this gauge field here with. Okay, so just assume you do the Lehmann-Zimmermann reduction. You try to pull out the gauge field from here into here. You have to have something to contract it with. There is nothing there, so therefore your 0th order term is 0. My 1st order term is non-zero, because I have a gauge field here, and that can be contracted with the gauge field that is contained in this external state. This gauge field can again be parameterized using some dynamical part in the polarization vector, and because I have to square the amplitude, in the end I get an epsilon square. I get 2 epsilons, and these 2 epsilons again get contracted with the 2 currents to the minimal coupling. The structure you obtain here is exactly the same as what we obtain for the virtual correction. You get again this factor. The integrals are a little bit different. Again, we have an MS bar prefactor. We have a d-dimensional integral, but this time, first of all, we have a sign difference. But we also have, yeah, and these order epsilon terms are a little bit different, but we don't need to care about them. Again, these are pure infrared singularities. We have a double pole, we have a single pole, and we have a log squared and some constant. Let's sum this up. We have double poles, single poles, finite pieces, but logarithmically enhanced, and we have constants. They are exactly the same between the virtual and the real corrections. They only differ in sign. The manifestation, what this is a manifestation of the KLN theorem. Okay, so you see the first explicit result of the KLN theorem here. That's the real virtual cancellation that everybody is talking about. It's made very explicit. And because we obtained this pole cancellation here between real and virtual from integrating over the full phase space, you can actually assign this to the endpoints. We can discuss this more in the recitation session, and remove the poles. And what remains are only the double logarithmic terms down here. And these terms do actually survive. When you add real and virtual, you see also unitarity. So what I derived very heuristically in the very beginning of the lecture, at the very beginning of the lecture, you see here explicitly from first principles, that the real and the virtual cancel precisely. And that's because of the simple structure of the theory. But let's say that your measurement breaks the unitarity by saying, for example, I want to veto the real radiation above a certain scale mu, then you will kind of kick out these terms and you will only be left with those, okay? In that case, the theory still has some knowledge about these poles. And the manifestation of this will be a double logarithmic enhancement of your cross-section at the scale at which you vetoed your real radiation. And that is very important. So what I'm encouraging you to do in the recitation session is to find more examples where this real virtual correction, where this real virtual interplay is violated by the measurement, and what the cross-section should therefore look like. Okay, the last thing, I think I will be going 1 minute over time, but this will be very important. So let me please finish this up, is to derive the all orders result for you in this very simple theory. So we already realized that the the first order contribution to the vacuum persistence amplitude is 0. And that was because we had only a single gauge field sandwiched between the vacuum states, and we have nothing to contract it with. The same is true for any odd order. It will also vanish, because for an odd number of gauge fields, I have always one gauge field left, then I cannot contract with anything. So only even contributions will contribute to the all orders vacuum persistence amplitude. And I can write the even contributions like so, like you see here on this line. And you may know how this thing is actually computed. I actually have to perform the Wick contractions of the gauge fields here. And for the first gauge field, I can find 2 n-1 partners in the Wick contraction. Afterwards, 2 gauge fields are done. Then for the next one, I can find 2 n-3 partners in the Wick contractions. Then 4 are done. And so it goes until I have 1. Remember, in the beginning, I pulled out a factor 1 over n factorial. So I'm putting this back here because this is very convenient. These terms can be canceled against certain terms in this 2n factorial. Okay. And after all is said and done, I can turn this factor into 1 over 2 to the n times n factorial times the basic integral, the second order result, to the power of n. So it's a very convenient structure. And if I sum it all up, I can turn the overall result into an exponential of the second order vacuum persistence amplitude. And that's quite remarkable, because what I have achieved is that I have derived the pseudocurve factor from first principles. Okay. In the beginning, we had the heuristic picture that the pseudocurve factor is just the kind of by unitarity determined result which we calculated from the real emission corrections. Now it's from first principles. And what you see is that it's actually the exponentiation of the second order virtual corrections. The resummed, as we call it, virtual corrections at the scale mu, if we work in dim rake MS bar. However, the logarithmic structure, as we have just seen, is exactly the same as for the real corrections. So if the theory is simple, let's say in abelian theory, we can also just replace this guy by the real corrections. By just taking the real corrections, as we saw, they just have the opposite sign and just instating the sign. And this is why the picture in the very beginning of the lecture is not as heuristic as it might at first have seemed. For abelian theories, it's actually exact. So the next exercise for you will be to discuss what is actually different in QCD. The other thing to take away from this lecture, and that is again very important, is this factor here. And we will discuss its analytic structure tomorrow. Okay, that's it. That's it for today.
Okay, thank you, Stefan. Are there some quick questions? We have a couple minutes before we, otherwise we can save it for the recitation. Okay, I don't see it at the moment, so I guess we'll save them for the recitation. So, yeah, thank you again, Stefan. And yeah, we'll take half an hour break, and we'll start on the half hour. So, all right, thank you very much.
Thanks a lot.